Okay, let's make a start. This is our final lesson. We're going to be talking about the final section, which is non-homogeneous linear systems. In this section, we're going to be considering equations like this. X prime is equal to some matrix P of Tx plus some vector function G of T, where we're going to assume that the matrix function and the vector function are continuous on some interval. Then the general solution of equation 1 can be written like this. First, we have the general solution to the homogeneous equation corresponding to 1. So in other words, that's x prime is equal to px. And then we also have plus a particular solution on the end. I'm going to talk about 4 methods which can be used to solve equation 1. We're going to talk about diagonalization. We'll talk about the method of undetermined coefficients. We will talk about using the method of variation of parameters. And we're going to use the Laplace transform. For each method, I'm going to do 2 examples. First method we should talk about is the method of diagonalization. We talked about this method for homogeneous equations. We can also use this for non-homogeneous equations. For example, consider this equation. X prime is equal to x plus g, where capital A is a square matrix of numbers. Let's suppose that A is a diagonalizable matrix. Let's suppose G is defined on some interval from alpha to beta. Let's suppose we call the eigenvectors of A xi1 up to xn, and let's suppose that T is a transition matrix, where the first column is the first eigenvector, second column is the second eigenvector, and so on. Then we know that if we calculate T inverse AT, we get a diagonal matrix where the entries on the main diagonal are the values of A. When we do diagonalization, the most important step, the whole point of the method, is we define a new variable y, which we say is T inverse x. Or to say this another way, we say that x is equal to ty. Then we can put this into our differential equation. Our differential equation is x prime is equal to ax plus g. X prime is the same as ty prime, and ax plus g is the same as aty plus g. Multiply both sides on the left by T inverse. We get y prime is equal to T inverse ATY plus T inverse G. Or we can write this as the diagonal matrix dy plus some new function h of t, where h is equal to T inverse G. We're going to solve this green equation. We're going to solve y prime is equal to dy plus h, and then we're going to change back to x. But y prime is equal to dy plus h is just this system. First equation is y1 prime is equal to r1 y1 plus h1. In this equation we have only y1 and t. These are the only variables in the first equation. The second equation, the second line, would be y2 prime is equal to r2 y2 plus y2 plus h2. There's no y1, no y3, etc. in this equation. There's only y2 and t here, and so on. Each one of these equations only has 2 variables, yn and t, in the final equation. That means we can solve each of these equations separately. We know how to solve first-order linear equations like this. According to the theory from chapter 2, yj of t must be e to the rjt multiplied by the integral of e to the power minus rjs h of s ds plus some constant cj e to the power rjt. We know this. As soon as we know y, we know x. That's the theory. Let's do two examples. First example, solve x prime is equal to minus 2, 1, 1 minus 2x plus 2e to the power minus t, 3t, which I'm going to call ax plus g. We need the eigenvalues and the eigenvectors of the matrix. Let me just tell you the eigenvalues are minus 3 and minus 1. The eigenvectors are 1, minus 1 and 1, 1. So we can write down the transition matrix T using the eigenvalues. That's 1, 1, minus 1, 1. First eigenvalue gives the first column. Second eigenvalue gives the second column. And we know how to take an inverse of a 2 by 2 matrix. So let me just tell you that T inverse is a half 1 minus 1, 1, 1. Here's the key step in the method of diagonalization. We define a new variable y to be T inverse x. So we start with x prime is equal to ax plus 2e to the power minus t 3t. That's the same as ty prime is equal to aty plus 2e to the power minus t 3t. And multiplying by t inverse, we get y prime is inverse aty plus t inverse of 2e to the power minus t 3t. And of course, this is the diagonal matrix minus 3, 0, 0, minus 1, y plus, and then when we calculate this, we get a half 2e to the power minus t minus 3t, 2e to the power minus t plus 3t. And that gives us our two first-order linear equations. y1, and I'm choosing to move the other y1 to the left, so it becomes plus 3y1 is equal to e to the power minus t minus 3 over 2t. And from the second line, y2 prime, again, move the y2 to the left, so it becomes plus y2 is equal to e to the power minus t plus 3 over 2t. We have two first-order linear equations, which we know how to solve. Because you know how to solve equations like this, let me just tell you the solutions. The solution to the first equation is y1 is equal to half e to the power minus t over 2 plus 1 over 6 plus some constant c1 e to the power minus 3t. And the solution to the second equation is y2 is equal to t e to the power minus t plus 3t over 2 minus 3 over 2 plus c2 e to the minus t, which I leave for you to check. As soon as we know y, we can find x, because x is equal to t multiplied by y. In other words, that's y1 plus y2 in the first position and minus y1 plus y2 in the second position. Add these functions together and simplify. We can write this as c1, vector 1 minus 1, e to the power minus 3t, plus c2, 1, 1, e to the power minus t, plus a half, 1 minus 1, e to the power minus t, plus 1, 1, t, e to the minus t, plus 1, 2, t, minus 1/3, 4, 5. Remember this solution, we'll come back to this later. Let's do another one. Solve x prime is equal to 1 root 3 minus 1x, plus the function et root 3 e to the power minus t. We need the eigenvalues and the eigenvectors, and then we write down the transition matrix T. T is 1 root 3 minus root 3, 1. And T inverse is 1 divided by the determinant of T. We swap the 1 and the 1, but they're the same. And we put a minus sign on the root 3 and on the minus root 3 to get a quarter minus root 3 over 4, root 3 over 4, a quarter. And of course, the diagonal matrix D, or T inverse AT, is just the diagonal matrix where the entries on the main diagonal are the eigenvalues. So minus 2, 0, 0, 2. That's the preliminary calculation now done. Now we can do the key step, the important step behind this method, which is to define y is equal to t inverse x. We always get y inverse is equal to dy plus t inverse g. And when we calculate that, that's the same as minus 2y1, 2y2 plus quarter e to the power t minus 3/4 e to the power minus t, root 3 over 4 e to the power t plus root 3 over 4 e to the power minus t, which I leave for you to check later. So we have two equations. y1 prime plus 2y1 is equal to a quarter e to the power t minus 3/4 e to the power minus t, and y2 prime minus 2y2 is equal to root 3 over 4 e to the power t plus root 3 over 4 e to the power minus t. We know how to solve first order linear equations like this, so let me just tell you the solutions. y1 is 1 over 12 e to the power t minus 3/4 e to the power minus t plus c1 e to the power minus 2t, and y2 is minus root 3 over 4 e to the power t minus root 3 over 12 e to the power minus t plus some constant c2 multiplied by e to the power 2t. Now we found y. The final step is to find the solution x. And the solution x is equal to t multiplied by y. I'm not going to finish this calculation. You know how to do this. I'll leave it for you to finish. The second method is the method of undetermined coefficients. This is an extension of the ideas that we used in chapter 3. Again, we're going to consider x prime is equal to ax plus g, where A is a square matrix of numbers. And the idea is this. First, we find the general solution to the homogeneous equation, x prime is equal to x. Then we need to find a particular solution. What we do is we look at, and we're going to make a guess with constants in, and we try to find the constants. And then step 3, we add our two functions together. For example, solve x prime is equal to minus 2, 1, 1 minus 2x, plus 2e to the power minus t 3t, which is an equation which we've already solved. We've solved this using the method of diagonalization. Now we're going to solve this using our new method. First, we solve the homogeneous equation. Let me just tell you that this is the solution. And then we need to find a particular solution. So what we do is we look at the function g. G is vector e to the power minus t plus vector t. Let's look at the second part first of all. We have a vector multiplied by a first order polynomial. We expect our particular solution to be similar somehow. We expect our particular solution to have vector t plus vector into it, for some vectors c and d which we don't know yet. For the first one, we have vector multiplied by e to the power minus t. And let me remind you that minus 1 is an eigenvalue of our matrix. So we can't just have vector e to the power minus t. We must multiply by t. A t e to the power minus t, and just so that it works, we're also going to add on b e to the power minus t. We need to find the vectors a, b, c, and d. So we calculate x prime is equal to x plus g. Put these functions in. X prime is a e to the power minus t minus a t e to the power minus t minus b e to the minus t plus c. Ax is this green term. Capital A small a t e to the power minus t plus capital A b e to the minus t plus capital A d. And I think there should be a t on the end. Yes. I guess it's gone off the edge of the page, but there should be a t here right on the end. We need to find the vectors a, b, c, and d. To do this, I'm going to look at each type of term. First, I want to look at the terms including t e to the power minus t. On the left, we have minus a t e to the power minus t, and on the right, there's capital A, small a t e to the power minus t. So we must have that minus a is equal to capital A. In other words, small a is an eigenvector. That means small a is a vector of the form alpha alpha, some number alpha, which we didn't find yet. Then I want to look at the e to the power minus t terms. On the left, there's a minus b multiplied by e to the power minus t. On the right, there's capital A b plus 20 multiplied by e to the power minus t. Now, we know that small a is a vector of the form alpha alpha. So on the left, we must have alpha minus 2 alpha, some number alpha, which we didn't find yet. On the right-hand side, we have a, b plus Is there a mistake here? Oh no, I'm getting ahead of myself. First, I'm going to rearrange the equation. 2, 0, I'm going to take over to the left, and this minus b, I'm taking over to the right. So I end up with a minus 2, 0 on the left, capital A plus IB on the right. And then, as I said, a minus 2, 0 is alpha minus 2 alpha. And on the right-hand side, we have a plus IB, which is the same as minus B1 plus B2, B1 minus. Now look, the first coordinate it's minus B1, second coordinate is B1 minus B2. These are the same except the second position is minus 1. Okay, as I've reconnected. On the right-hand side, I have minus B plus B2, and B1 minus B2. But these are the same except that the second coordinate is minus 1 multiplied by the first coordinate. That means over on the left, alpha minus 2 must be the same as minus 1 multiplied by alpha, which means that alpha must be equal to 1. And after we know alpha, we can choose b. B must be of the form k minus 1. At this point, we've finished looking at the e to the power minus t term, so it's okay to choose whichever value of k we want. I choose k is equal to 0, and I get b is equal to 0 minus 1. Next, we need to find c and d. If we look at the t terms, on the left-hand side, there are no t terms. On the right-hand side, we have capital A small c plus 0, 3. We can rearrange this to find that c is A inverse, 0 minus 3, or 1, 2. And finally, we can look at the terms involving 1. On the left, I have small c multiplied by 1, and on the right, I have AD multiplied by 1. We know c, d must be A inverse c, or minus 4 over 3 minus 5 over 3. We found A, B, C, and D, so now we know our particular solution V. We can finish our example by adding together our two functions. That's the general solution to the homogeneous equation plus V. And this is exactly the same solution that we found using the method of diagonalization. Another example. Solve x prime is equal to 2, 3, 4, 1x plus e to the power t minus 10t minus 3. we go through this quickly. We need the eigenvalues and the eigenvectors, and then we can write down the general solution to the homogeneous equation. Then we need to find a particular solution. So I'm going to do this in two different steps. First, I'm going to find a particular solution to this equation, and then we'll find a particular solution to another equation, and then we'll add everything together. Because number 1 is not an eigenvector of our matrix, we don't need to consider t e to the power t. Instead, we can just look at the ansatz a e to the power t for some number, some vector small a. And then put this into the equation. We can find that a1 must be 0 and a2 must be minus 1/3, which I will leave for you to check. So we have the particular solution, x is equal to 0 minus 1/3 e to the power t. Then I want to find a particular solution to this equation. X prime is equal to 2341x plus 0 minus 10t minus 3. We need to make a guess at the solution. So what we do is we look at this function. We have first order polynomial here, so we expect our ansatz to have a first order polynomial. So we're going to guess that x is equal to at plus b for some vectors a and b. We put this into the solution and we find a linear system. We solve the linear system and we find that a must be 3 minus 2 and b must be 0, 1. So our particular solution is 3t 1 minus 2t. And then finally, we have three functions. If we add these together, we get the general solution to the differential equation that we were asked to solve. In blue, I have the general solution to the homogeneous equation. And then in orange, I have our first particular solution. And then in green, I have our second particular solution. Add these all together, we get the answer. Method 3 is the method of variation of parameters. This time it can be a little bit more general. Instead of a matrix of numbers, let's suppose PT is a matrix of functions. Let's suppose a matrix of continuous functions. And let's suppose that there exists a fundamental matrix, capital Xi, for the homogeneous system x prime is equal to px. Then we know that the general solution to the homogeneous equation is x is equal to the fundamental matrix, capital Psi, multiplied by a constant vector c. The idea behind variation of parameters is we guess that if we replace the constant vector c by some very special function u of t, then we can get the solution to the non-homogeneous equation. Then the key question is, can we find this function u? What we do is we take our guess, x is equal to psi u, and we put this into the differential equation. On the left, we get xi prime u plus xi u prime, and on the right, p xi u plus g. But remember, an important theorem from last week an important thing which I said that you should prove yourself, and there's an exercise in the lecture notes which asks you to prove this. If we have a fundamental matrix for a homogeneous equation, then this fundamental matrix solves the same equation. In other words, capital Psi solves psi prime is equal to p psi. Look at the top again, we have psi prime u on the left, p psi u on the right. These must be equal, so we must be able to cancel these out. Then our equation simplifies to psi u prime is equal to g. Psi must be invertible, so u prime is equal to psi inverse g, and u must be the integral of this function. And then we can finish by multiplying by psi. So the formula for this method is that the solution x is equal to psi multiplied by the integral of psi inverse g. So let's just recap. To use the method of variation of parameters to solve x prime is equal to px plus g, we need to find a fundamental matrix for the homogeneous equation x prime is equal to px, and then we use this formula to calculate x. Let's go back to our friend. Solve x prime is equal to minus 2, 1, 1, minus 2x plus 2e to the power minus t, 3t. This is an equation we've already solved 2 times. First, we need a fundamental matrix for the homogeneous equation. Because the general solution of the homogeneous equation is this, we can write down a fundamental matrix. Fundamental matrix is left column e to the power minus 3t minus e to the power minus 3t, and right column e to the power minus t e to the power minus t. We need the inverse of this matrix. I'll leave it for you to check that this is the inverse of the fundamental matrix. And we need to calculate the integral of psi inverse multiplied by g. And again, I leave it for you to check that this is the correct calculation. And then we're almost finished. You can write down the solution to the non-homogeneous equation just by multiplying the fundamental matrix psi by this integral. And I'm going to leave it for you to check this correct calculation. Check that we get this solution, which is exactly the same solution that we found using the previous 2 methods. A second example for variation of parameters. Solve x prime is equal to minus 4, 2, 2, minus 1x plus t inverse 2t inverse plus 4. Where just because I don't want to worry about 1 divided by 0, we're going to say that t is always positive. We need the eigenvalues and the eigenvectors, and then we can write down a fundamental matrix for the homogeneous equation. Then we need to find the inverse of this fundamental matrix. I'll leave it for you to check that we get 1 over 5, 1, 2, minus 2 e to the power 5t, e to the power 5t. And we can calculate xi inverse multiplied by g. Again, please check that we get t inverse plus 8 over 5, 4 over 5 e to the power 5t. We need to integrate this function. Integrate this with respect to t, we get ln t plus 8 over 5t plus some constant c1, 4 over 25 e to the power 5t plus some constant c2. And then the final step is to multiply this integral on the left by the fundamental matrix. You can check that the solution to this equation is c1, 1, 2 plus c2 minus 2, 1 e to the power minus 5t plus 1 to ln t plus 8 over 5, 1, 2t plus 4 over 25 minus 2, 1. And then we come to our fourth and final method. We can use the Laplace transform to solve non-homogeneous linear systems. Before I go on, I need some notation. If small bold x is this vector, then by capital X, I mean the Laplace transform of small x. And all that means is we take the Laplace transform of each coordinate. Laplace transform of x1, Laplace transform of x2, and so on. We studied the Laplace transform in, would have been chapter 4. We know that the Laplace transform of y prime for some real valued function y is s multiplied by capital Y minus y0. We have almost exactly the same formula for the Laplace transform of vectors. Straight away, you're probably guessing, and you would be correct. The Laplace transform of x prime is equal to s capital X minus x at 0. And this is true because all we're doing is we're taking the Laplace transform of each coordinate, so the same rules apply. Solve an initial value problem. Solve x prime is equal to minus 2, 1, 1 minus 2x plus 2 e to the power minus t, 3t, with the initial condition x of 0 is equal to 0. We've solved this equation 3 times already. Now we're going to solve it again. When we use the Laplace transform, we want to use an initial condition. So this time, instead of just solving a differential equation and finding a general solution, this time we're going to solve an initial value problem. What we do is take the Laplace transforms of the differential equation. On the left side, we have the Laplace transform of x prime, which by the theorem is the same as s capital X minus x at 0. And on the right side, we have the Laplace transform of a small x plus small g. That's A. A is just a matrix of numbers. That's not going to change. Laplace transform of small x is capital X. And for the Laplace transform of small g, we'll call this capital G. And you can check that capital G is 2 over s plus 1, 3 over s squared. Because we're using the initial condition x of 0 is the 0 vector, what we have is si minus a capital X is equal to g. Or capital X is si minus a inverse multiplied by g. What is si minus a inverse? We can calculate this like this, and then we can multiply this by g to get this complicated looking vector function, which I leave for you to check. Then we want to take the inverse Laplace transform of this. There's nothing mysterious going on here. We just use the techniques that we've used before, partial fractions, etc. Find the inverse Laplace transform, and we find our solution. For an equation like this, perhaps the Laplace transform is the most difficult method or longest method, but of course the Laplace transform method is more powerful because we can use that for piecewise discontinuous functions, piecewise continuous functions. One more example, and this is the final example of today's lesson, so the final example of this course. Solve 2x prime plus y prime minus y minus t is equal to 0. X prime plus y prime minus t squared is equal to 0. X of 0 is equal to 1. Y of 0 is equal to 0. This is a little bit complicated at first look. We have both x and y in each equation. We also, say that again, we also have x prime and y prime in each equation, which is something we haven't seen before, but it's not a problem. We can solve these equations for x prime and y prime, and we get x prime is equal to y minus t squared plus t, y prime is equal to minus y plus 2t squared minus t. I leave this for you to check. If we write this in terms of matrices, we get x prime is equal to 0, 1, 0, minus 1, x plus t minus t squared, 2t squared minus t, with the initial condition x of 0 is equal to 1, 0. I want to solve this using the Laplace transform. So I take the Laplace transform of the differential equation, rearrange it, I leave this for you to check. I get si minus ax on the left, small x of 0 plus capital G on the right. Which, if we put the numbers in, is s minus 1, 0, s plus 1 capital X, plus 1, 0, plus 1 over s squared minus 2 over s cubed, 4 over s cubed minus 1 over s squared. And therefore, we can find a formula for capital X. After we know capital X, we can take the inverse Laplace transform. We need partial fractions, check that these are correct, and then take the inverse Laplace transforms to find the solution to the initial value problem. I think it's better if you read through these calculations when you have time. We find that the solution to the initial value problem is x is equal to 5 e to the power minus t minus 4 plus 5t minus 2t squared plus 1/3 t cubed, and then minus 5 e to the power minus t plus 5 minus 5t plus 2t squared. There's nothing new in this calculation, it's just using the ideas from the previous chapter about the Laplace transform. And we come to the end of this course. Do you have any questions? Okay, so all the homework is available. I've changed the deadline to the day before the exam. After the homework deadline, the answers will be revealed. Hopefully that will help you. If you have any questions between now and the exam, of course, you can ask me on the discussion forum if it's not private, or by email if it's a private question. If there's demand for it, we can have an online office hour like this, but that's up to you. You're welcome to leave whenever you wish.